Hey everybody, welcome back. Thanks for checking out the Lesson 10 lecture today. Lesson 10 is talking about transforming three-dimensional integrals, which we started with two-dimensional integrals in last chapter. Now we're going to transform 3D integrals. Okay, transforming 3D integrals is a lot like transforming 2D integrals in the last unit. For three-dimensional integrals, the equivalent of what we said, the area conversion factor of xy, is the volume conversion factor xyz. So how do we find the volume conversion factor? It's just the absolute value of the determinant of this matrix. Okay? So first you take the derivative of x with respect to each three variables. Second row is the derivative of y with respect to each three variables. And the last row is the derivative of z with respect to each three variables. So let's take a look at how one works. Find the value of the triple integral above the region R of x, y, z of x over 4 squared plus y over 1 squared, where the region R is the region bounded by the ellipse x over 4 squared plus y over 1 squared equals 1, with bottom z equals 0 and top z equals 3. All right, so the first thing we're going to do is we're going to change this ellipse into polar coordinates. All right, we're going to let x of RST equal 4r cosine t. Y of RST is equal to 1r sine t, or just r sine t. And then z is just going to be our s. And we're going to let the radius r go from 0 to 1. Our s, we're told where that should go. It should go from 0 to 3. It says bottom z equals 0, top z equals 3. And we're going to let our t run from 0 to 2 pi. All right, so before we can set up our integral, we need to find our volume conversion factor. Okay, so for our volume conversion factor here, we're going to set up our 3 by 3 matrix and find the absolute value of the determinant of that matrix. Okay, so first, the derivative of x with respect to r, s, and t. And that would give us 4 cosine t, 0, and negative 4r sine t. Now the derivative of y with respect to r, s, and t. And that would be sine t, 0, and r cosine t. Now the derivative of s. And that would be, z with respect to s here. And that would be 0, 1, and 0. So the derivative of z with respect to r is 0, with respect to s is 1, and derivative of z with respect to t is 0. I'm just going to make that a little bit smaller here so I have room to work. Okay, and then what I like to do is take these first two rows, just copy and paste them out here. And we can run through our determinant this way. All right, so it's the absolute value. Remember, we're just going to multiply this way first, and then subtracting this way. So it's the absolute value of 0 plus 0 minus 4r sine squared minus 0 plus 4r cosine squared plus 0. Okay, simplifying that, we get absolute value of negative 4r sine squared minus 4r cosine squared. And if we take a negative 4 out, we'll have sine squared plus cosine squared. So it's just the absolute value of negative 4r, which is, of course, just 4r. As long as r is positive, which is running from 0 to 1. So it has to be positive. So our volume conversion factor here is simply 4r. Since r will always be positive, 4r will always be positive. Okay, now we can set up our integral, our triple integral. All right, so we'll do 0 to 2 pi, 0 to 3, and 0 to 1. Remember, you can do that in any order. It doesn't really matter. Of x over 4 squared, so that would be 4r cosine t over 4 squared plus y over 1 squared, so that would just be r sine t squared times our volume conversion factor 4r dr ds dt is the order I have it set up in. All right, before we do any integration, in the first term there, 4 over 4 canceled, so we're left with r cosine squared, which is going to be r squared cosine squared, and then plus r squared sine squared times 4r, and a little bit more simplifying before we can actually do our integrals. That would just leave us with r squared times 4r, which is 4r cubed, which looks a whole lot nicer than where we started. Okay, so taking the antiderivative with respect to r is r to the 4th over 4 times 4, so that would be r to the 4th from 0 to 1. If you substitute the 1 and the 0 in and subtract them, you simply get 1. Now taking the antiderivative with respect to s, so 0 to 2 pi of s from 0 to 3 dt. Put 3 and 0 in, subtract. You get 3 dt. And then one more antiderivative, we get 3t from 0 to 2 pi. Put 2 pi and 0 in and subtract, and we get our final answer to be 6 pi. So the volume of that integrand above that region is 6 pi. Another example here, calculate the triple integral above the region R of z for the region R bounded by the xy plane, the xz plane, the yz plane, and this function here, z equals 6 minus 3x minus 2y. All right, so I'm just going to start by copying that down here. Z equals 6 minus 3x minus 2y. All right, so what I'm going to do first here is I'm going to solve that equation for x. So z minus 6 plus 2y over 3 would give me x, or if you want to simplify it a little bit, z over 3 minus 2 plus 2/3 y. All right, because we're using all the planes as bounds here, at some point x and y and z will all be 0. Okay, so right now, let's let the x be 0. And solve this for y so we can get our other intersection point here. All right, so if I multiply through by 3, and solve that for y, we get 6 minus z over 2 equals y. Or again, if you want to rewrite that, you can write it as 3 minus z over 2. All right, so now, like I said before, everything's got to be 0 at some point since we're using all the planes as bounds. So now let's let y also equal 0. If we solve that for z, right, and z could also be 0 because that's also the third bound by all the planes that we're bounding this region by. All right, so now we have all of our top bounds. Z would be 6, y would be 3 minus z over 2, and x would be z over 3 minus 2 plus 2/3 y. Okay, or you can use the other unsimplified versions as well. All right, so now we can set up our integral. I'm going to do dx, dy, dz, so we'll work from dz. And so the bounds for z are 0 to 6. The bounds for y are 0 to 3 minus z over 2. And the bounds for x are 0 to, I'm going to rewrite that a little bit, so 2 minus 2/3 y minus 1/3 z. Of z dx, dy, dz. All right, we really don't need to do any conversion here because we were able to find the bounds this way. All right, now I've already walked through all the steps of this. You can at any point here pause the video if you need to see what you're doing, but I'd like you to actually try this triple integral on your own. And as you go through it, you could pause the video and check your next step and see if your work is correct. But I'm just going to kind of scroll through, and again, like I said, you can pause the video at any point to check your work. The next step, substituting the bounds, simplifying, taking the antiderivative with respect to y, substituting in the bounds, lots of simplifying, lots more simplifying. Should get down to here, and we combine like terms, which is right over here. And then we can take our antiderivative with respect to z, which is what we get over here. And then we can substitute in 6 and 0. And we end up getting 9 as our final answer. So the volume of that region, of z above that region would be 9. All right, last problem here. We have a triple integral that we're going to try to rewrite in a couple different ways. The triple integral -1 to 1, y squared to 1, 0 to 1 minus x of 1 dz dx dy gives a volume of region T that is bounded by the parabolic cylinder x equals y squared and the plane z equals 0 and x plus z equals 1. So the question asks us to rewrite this triple integral in two different ways and compute all three integrals to verify they are equivalent. All right, I will leave the computing to you. I will show you how we can rewrite this in a couple different ways. Now, technically, there are 6 different ways to write this integral. All right, if you just talk about computations, putting x, y, and z in certain orders, you can pick 3 for the first slot, 2 for the second slot, and 1 for the last slot. 3 times 2 times 1 is 6. So we could do this 6 different ways, but the problem is just asking us to do it in 2 other ways, which will give us 3 of these 6 possible ways. Okay? You see a picture I have drawn there. It's kind of a picture of this region that we're looking at. All right, so the first thing we're going to do here is we're going to say, all right, I know that since x equals y squared, I know that y equals plus or minus root x, right? I'm going to write that down here a little bit so I have more room. Y equals plus or minus square root of x. Okay, and then I also know that since x plus z equals 0, z equals 1 minus x. So I'm just trying to get everything in terms of x's here. And now I can write my triple integral as such. We can go the integral from negative root x to root x dy In front of that, the integral from 0 to 1 minus x dz. And in front of that, the integral from 0 to 1 dx. So that's one way, one other way we could do this. Starting over again. Another way we could do this is we can say, all right, I know that right here, let's do a different color this time. I know that x equals 1 minus z, right? And from here, since x equals y squared, we can say 1 minus z equals y squared, or z equals 1 minus y squared, which then z we can say is root 1 minus y squared, plus or minus the root of 1 minus y squared. So our x bounds, if we're trying to put everything here in terms of x here, we can say our x bounds are going to range from y squared to 1 minus z. All right, that's what we got right here to right here. And that's our dx bounds here. Z, we know, is going to be 0. And then what we have up here to 1 minus x. And then our y coordinates, by doing some computation, we go from 0 to 1. Okay, that's another option we can use. I do actually have a third option written down that I can write down here for you as well if you want to see a third way of doing it. Maybe you can try to figure out how I came up with this third method. Like I said, there's actually 6 orders of integration here. What you have on this sheet here is 4. 4 of the 6 possibilities. There are 2 other ones as well. Maybe you can try to find those other 2 for extra practice. All right, that's the end of our Lesson 10 lecture video. If you have any questions, you can always feel free to ask me during class. Thanks again for checking in, and have a good rest of your day.